Hello, welcome to another episode of Flying High with Flutter. I'm your host, Alan Wyma. And today we have a very interesting, amazing guest, Dominik. Dominik, I believe it's Tornow. I never actually asked how to say your name. Hopefully I got that right. He wrote this
You
interesting
got that
book.
right. First
Okay.
try.
I'm happy that I didn't do it wrong this time, at least. Maybe next time. But he wrote a very interesting book that resonates a lot with me called Think Distributed Systems. And that's also I want to bring you on because people are actually working with distributed systems more than they think. Distributed system sounds like a very scary thing, but if we were talking before the show, like if you have an API server and you have a database, you already have a distributed system, right?
Yeah.
So
All modern systems today are distributed systems, right? It's not a question if your system is distributed. It's only a question to what degree your system is distributed. It can be more distributed or it can be less distributed, but chances are really high it will be distributed.
well, that's something I think is quite interesting too, because I mean, how do we even start? Actually, maybe why don't we start from the beginning? Who are you, and why are you somebody that Manning thinks is really a great authority on distributed systems, and what made you decide to write this book? Maybe we can talk more about your background first, and kind of lead into the book and how you got started with that, if you don't mind.
Well, okay, I go back to the beginning, but I'm going to try to keep it fairly brief. So I came to the United States for an internship the first time in 2006. And then I permanently relocated to the United States in 2008. And that was also my entry into the industrial world of software engineering. And that was for me a great time to join because 2006 was not only like significant for me personally coming to the United States as an intern and joining a large company, SAP, but it was also a transformational year for the ecosystem at large because 2006 was the year that the cloud was born. In, I believe, March 2006, AWS released S3, and in August, if I'm not mistaken, of 2006, US released EC2. So that was basically the birth year of the cloud. And with that, my entire career went basically in lockstep with cloud applications. And cloud applications are distributed applications. And I also caught the distributed system bug. I was fascinated by the problems that were presented by a distributed systems. So I leaned into that heavy out of personal curiosity. Right? So I leaned into that, and then as a ecosystem developed, right? Just like when it comes to distributed systems, when it comes to distributed databases, and then mobile applications. I basically like developed my career around that development as well.
It's interesting. I forgot about the kind of the birth of cloud, because to me, cloud is mostly like a marketing term. Are you on the cloud? But yeah, now it's a little bit less marketing than it used to be. But kind of coming back to that, right? It's interesting. You also worked a little bit with mobile apps because that's what we mostly do with Flutter. So it's good to kind of to talk about that. Now, I was just kind of taking a look at your book a little bit earlier today, and I like the way that you kind of laid out the content in terms of thinking about a system where it's like an office building of people, right? And because usually people are, okay, this company Microsoft, and now it's OpenAI, NVIDIA, they're doing this, they're doing that. Actually, not entirely. It's like, even your body, right? Basically everything in the world has got a lot of concurrent actors or processes or systems, or in this case of people doing different things that somehow make up a larger thing, right? Like Facebook is like one thing, but then in there, of course, you have uploading photos, making comments. Each of those is kind of like a concurrent different thing, right? I really love that idea of how you kind of laid that out. Do you mind to kind of talk a little bit more about that? Because I think that makes it much easier to understand about how to think about your system. And I really love that the way you did that.
So for this, so I like to break like large concepts down into very fundamental building blocks. Sometimes that is called thinking from first principle. because then if you boil it down to the very essence, you have the building blocks that you can use to reason about your system. So when we think about distributed systems, there are really two forces at play. Two. And one is concurrency. Concurrency is defined by a non-deterministic partial order. You just don't know what is going to happen next. And then there is distribution. And distribution is defined by non-deterministic partial failure. You don't know what fails next. Right? And that is basically the playing field of distributed systems. But sometimes that feels a bit abstract. So I was looking for an analogy that is not only tangible, but also correct. It correctly reflects distributed systems, not only to a certain degree, but really to 100%. And that's what, when I settled on the office building. So I was thinking about, there is an office building and there are multiple offices, so multiple rooms in this building. And every room is occupied by one person. And that person cannot simply communicate with others by just picking up the phone or by yelling across the floor, but they have to send letters to each other. And I was reminded of this old-timey communication device that they had, the pneumatic tubes. Right? I mean, they do predate me, but I saw them in a few movies where you're basically able to have like a little container. You put the letter in the container, you put it in that tube, and then this goes to a mailroom, and there's a mailroom attendant, and that mailroom attendant then looks at addressee and puts the container into the tube for the addressee. So now the addressee gets your letter. And that is a very accurate way of reflecting distributed systems. Because if you look, what is a distributed system? A distributed system is a collection of concurrent components. They have exclusive access to their own state. So state is not shared. And they have exclusive access to a channel to the network. And they communicate by exchanging messages over the network. And if we now map that to the office building, that's now the same situation, right? So we have the office worker. One office worker is in the room, and that office worker has access to local storage, has for example a notepad, but it's his or her notepad, right? Nobody else can look at it and write on it. And then they're able to send letters to each other. And that's how they communicate and share information. And now we can actually start using that analogy to reason about like different things, different situations that can happen in the building. So first off, as with a distributed system, right, a company is not just like a group of people, but it's a group of people with a mission. So they all need to collaborate. So that basically means they need to coordination. Right? So they need to coordinate. So far, so good. They can send messages to each other to coordinate. For example, they could do something very benign, like coordinate where to go for lunch. That is not necessarily like contributing to the company's mission, but it's like still a vital part of being an office worker. So let's coordinate where to go to lunch. If you have guarantees around delivery times for your messages, and you have guarantees that your message will be delivered, right? And you have the guarantees that your coworkers will all correspond timely to your message, it's actually fairly easy to coordinate that. Right? And that is what we call the synchronous system model with strong guarantees, basically the absence of any failure. But if you don't have these guarantees, for example, we could have Bob, the mailroom attendant, who is a super nice guy, but is not like It's a little disorganized. Once in a while, he forgets to send out a message. Right? Then, well, did my colleague receive my message? And my colleague knows when and where we're going to meet for lunch? I just didn't receive his response? Or did my colleague not get the message? And therefore, I'm in front of that restaurant waiting, and my colleague's never going to show up because he thinks, hey, Dominik didn't send me a message. That's what we generally call an asynchronous system model in the presence of failure. And with this analogy, you can make something very tangible and map these distributed system problems onto a domain that is fairly straightforward to reason about because we can relate to it. And then over time, that analogy becomes less important because you're going to develop this distributed systems brain. Right? You're gonna think about these situations. Well, what happens if my component, my process, my node sends a message, but the message doesn't arrive? What happens if my component, process, or node crashes? Then you don't need to map it onto this analogy. But especially when getting started, or when trying to think about very, very complex situations, complex interleavings, right? Then it helps to just map it onto something that we are so comfortable with because it's just like our life, our lived experience, yet it is accurate. So that's why I like this analogy a lot, the distributed systems Inc.
Yeah, and I love that you use the tubes, right, and how they connect and how they talk to each other. I mean, obviously, not every single system needs to use some kind of network protocol to talk to each other with a distributed system. There's different ways you could do it. I mean, there's like with Unix, like you have piping. You can use some kind of IPC interprocess communication, I think it's called. You can use a message bus. I mean, there's so many different ways that you can do it. I mean, technically, it's going back to our same model before, right? If you have your app server and you have your database, you're using that database driver in between, right? That kind of protocol. So it's really quite interesting. But kind of
You need
yeah, go
you
ahead.
need the tube. You cannot use a phone. Because when we are on a phone call, right, we know the other person is there. We know the other person is talking to us. It is real time, right? So we have a much, much stronger knowledge about the current state of the system than we have when we exchange messages. And there is something incredibly interesting here, and that is this shift in perspective. Think about being in that office building. When you are in that office building, there is only you, and then there is the rest of the world. Right? There is not necessarily Bob and Eve. You have a container and you write Bob on it, right? And you put that container onto the network. But who is actually going to send you an answer if they do? Right? It's only an initial addressing. It's only basically a suggestion. And we know that this indirection, for example, if instead of Bob, I write on it HR, right? Send it to anybody in HR. I don't know anything about HR, right? And that is a very interesting perspective. That is, every component very much exists in isolation. And from that component, there is only itself and the rest of the system. So it doesn't actually, one component doesn't really talk to another component. It just talks to the rest of the system. And that's a super interesting perspective. And there is this asymmetry of information. When we look at a distributed systems diagram, right, we often look at it from a godlike perspective, right? We look at it and we can observe the entire state on our whiteboard, right? This illustrated state on our whiteboard all at once. No single component in the system has that possibility. Every component can only look at their own local state and then can communicate with other components or basically with the rest of the system if it wants to learn about any state outside of its own. And as soon as it learns about that state may already be outdated. So it's a very different perspective from how we often think about distributed systems in this godlike perspective, right? I know what's in the browser, I know what's in the database, but neither the components running in the browser nor the database have this immediate view of the state of the world without communicating, sharing information, and the possibility of that information being outdated. So it's a very, very, very cool analogy that, for example, if you just model it by, hey, let's have a phone call, doesn't work anymore. It has to be the nomadic tubes and it has to be exchanging messages.
Yeah, I like that you're talking about like exchanging messages because as we talked about before the show, both of you and I worked with Elixir, and that's a very much an interesting perspective, right? Like that's one of the most, I don't know, it's got distribution kind of at the core of it. I'm not sure if it's the most, but definitely one of the ones, I mean, more than most other languages I can think of. And it's funny because they always talk about message passing, right? Everything, you only communicate two processes. So coming back to your analogy, right? You have for your office worker, that would be a process in terms of Erlang and Elixir terms. And actually within Flutter, we have Dart language. I'm not sure how much you know about Dart, which is the language that backs Flutter, but Dart is actually modeled on Erlang, which I actually heard from one of the creators, where they actually do have the same idea as a process, but they call it something else. I forgot what the term is off the top of my head. And they also do message passing too, which is quite interesting. I think people don't know how powerful it is because people are so used to, okay, let's just pass a reference, or I want to use this variable in a thread, and they don't think about locking and all these kinds of crazy things. So much of what you said like really just rings in my head like, yes, I know about this. Yes, yes, this is a problem. Yes, this is totally true. And you also remind me of that old like the three triangle issue that that you have with, is that distributed systems? I think it is, right? Where it's like you have like, it could be correct, it could be, okay, sorry, CAP theorem. I think you know CAP theorem.
Oh, the
right?
CAP theorem.
Yeah.
Yes.
Do you mind to kind of go over
Oh,
that? Because
I have very strong feelings about the CAP theorem.
Please talk more about CAP theorem because that's a very powerful thing, and people never really think about this problem. And it's something that you have to think about if you have a highly distributed system. Is you need to figure there's trade-offs for that kind of stuff. And CAP theorem is basically talks about all those different things. If you don't mind to talk a little bit more about it, especially since you're so strongly opinionated about it.
Very, very, very strong. I don't have only positive feelings towards the CAP theorem. And I also spent quite some time in my book talking about the CAP theorem, and also on formerly Twitter, now X. And so there are two versions of CAP, which is short for consistency and availability and partitioning. And there are two versions of it. There is the original version, which is a CAP conjecture, just basically just best guess. Yeah? And then there is a later version, which is the CAP theorem, which is it's a formal proof. Now, the CAP conjecture is fairly tangible, but it's not a theorem. And the CAP theorem is a theorem, but neither tangible nor practical. So CAP is first often misunderstood as 2 out of 3. So you can choose, for example, consistency and partitioning, and then you have to forego availability. Or you can choose consistency and availability, and then you have to forego partitioning. So this 2 out of 3 narrative is already incorrect. Because partitioning, the situation where two components cannot exchange messages over a network, two or more, can temporarily not exchange messages over the network, is not something to choose. That is just a reality. It's something that happens. Right? So P is fixed. The possibility of partitions is fixed. Now, the CAP conjecture basically states, well, now you have to choose between consistency and availability. And I purposefully not define consistency and availability right now. So you have to choose between consistency and availability. You cannot have both. That's what the CAP conjecture states. And then a few years later, when the CAP theorem was basically formally proven, it is it is a proof of the CAP theorem, but it is completely impractical and misses the mark. So in the CAP theorem, consistency is defined as linearizability of a read-write register. Meaning that if I have replicated a register, like a variable, right? I have a variable variable X on server 1. Let's make this super simple, right? It doesn't even have to be a database. Just one variable. We just store one value on server 1 and a variable X on server 2. Right? That means that, like, if I write the variable, if let's say it's initialized to 0 and then I write the value 2, right? That on the next read, I shall receive the value 2. And availability means that the read and write request, they both receive an answer, right? It's not that it's just like sitting there forever. Now, the system model of the CAP theorem is, while itself correct, it's formally proven, is like completely unrealistic and not practical. Because what that system model states is that any server must be able to respond, right? Any server. So what they basically did is they said, well, just imagine you have a network partition that partitions server 1 from server 2. Now on server 1, I set the value from 0 to 2. Now I want to read from server 2 the value, but then I get the value 0, right? Because there's a network partition and they cannot synchronize the data. And with that proof, yes, totally true, right? Completely impractical. Doesn't matter. So while the CAP conjecture, it did something. It did something. It basically communicated to us as an ecosystem. In distributed systems, there are trade-offs. You cannot have both, right? Or let's say in a different way, often properties, they are in conflict. For example, if you want a scalable system and a reliable system, the more reliable it is, the less scalable it may be. Right? There are conflicts. We have to make the trade-offs. But CAP is not a great tool to reason about these conflicts. Because again, the CAP conjecture is tangible and practical, but it's not a theorem. It's basically just like a gut feeling. And the theorem itself is a theorem, but it's neither practical nor tangible.
That's interesting because like I always thought CAP theorem kind of made sense, right? Because if you think about it, like in terms of consistency and availability, I mean, if you have a distributed system with data, how can you kind of have that where it's like, well, obviously being available would mean that data to have best availability, you want to have data in different places. But then consistency would be a problem because you can't keep the same data always up to date. There's going to be some kind of delay usually, right?
On the CAP theorem, we strongly require, right? That is how the theorem was defined. We strongly require that any server must be able to respond. Any, right? That is an impractical requirement. So, and then we go, for example, to distributed consensus, where we have 3 servers. As long as at least 2 out of these 3 are able to communicate, we can make progress. So therefore, you can say we already basically broke the CAP theorem. Well, no, we don't, because now we just don't require any server to be able to respond. But again, this is already not a practical requirement. Why would you want that? Like 2 out of 3 is great, because now we can actually compensate for the failure of a node. If we have 5 nodes, we can compensate for the failure of 2 nodes, and so on. If we have 7, we can compensate for the failure of 3. So then we can already guarantee both consistency and availability, right? Even in the presence of failure and network partitions, as long as the majority, the quorum, is able to communicate. And that is for me, that is a true breakthrough, right? The notion of, or the concept and algorithms around distributed consensus, that is a real breakthrough. CAP is basically, as Martin Kleppmann said, it's like, it's time to retire the poor thing and think about the world in different terms. I do want to give the CAP conjecture the credit that it made sure that we all start thinking about the trade-offs that are present in distributed systems.
Okay. But there was something I was just having some. Sorry, I'm just going to switch a topic because we talked about CAP theorem and CAP conjecture for quite some time.
Yeah, no.
In your book, you talk a little bit about this idea of liveness versus is it
Safety.
correctness? Safety. Yeah, yeah. Do you mind to talk about that? Because that was a little bit difficult concept for me to understand when I read it a couple times, but it was starting to kind of click.
To go back a few steps. So like early in my career, I did struggle with what are the tools to find true understanding, right? So I was consuming in my workplace whatever I was working on, consuming as much as I could. There were like company internal, there were like blueprints and technical documents, then also external blog posts and videos on YouTube. And I was trying to get like a true dependable understanding, because for me there's nothing more uncomfortable than uncertainty, because when I'm uncertain I'm not confident, and when I'm certain I'm confident, and when I'm confident it's just a great feeling. That's basically my happy spot. I want to be confident in reasoning about the systems. So I was looking for a tool set. It's like, how do I think about these systems? Right? What even is a system? What even is a distributed system? How do you describe it? How do you even say that a system is correct? Right? Because at the end of the day, software is what software does. Right? If my process crashes in the middle, is it correct? Now, generally we say no, but why? Right? I was like, why is that not the correct behavior? Right? And then eventually I came across a book specifying systems from Leslie Lamport, which introduces a TLA plus, the temporal logic of actions. Man, it's a tough read. It is really a tough read. I read a lot of like supplemental like material. There was also another book by Hillel. It's like about TLA plus that was talking a bit less theoretical and a bit more practical oriented. So I took a lot of that in, and that temporal logic of actions is basically a formal method, right? So thinking about systems formally. And I always thought, well, formal methods, that's basically like how you prove a system correct, and they're all completely impractical. Right? But then it turned out it was like it's actually not at all what formal methods are. Yes, you can use them to prove a system's correct. But what they are first and foremost is a thinking tool. Right? They allow you to think about like very complex systems on a very abstract level, focusing on only the aspects that you want to focus on. And one of those aspects is, how do you even define correctness? When is a system correct? And there turns out that any property about a system, any, and that is formally proven, but I do not understand that proof. It's very tough. But it turns out that any property of a system is a combination of safety properties and liveness properties. A safety property is a property that guarantees that nothing bad is ever going to happen. And a liveness property is a guarantee that guarantees that something good is eventually going to happen. And we can look at, for example, distributed transactions for exploring safety and liveness. If you have a distributed transaction, we have two transaction participants, right? Participant one, participant two. Now, a safety and they both must commit, or they both must abort, right? That's basically the definition of a transaction. So a safety property states that it must never happen that one participant aborts and another participant commits. Right? Nothing bad must ever happen. That would be bad. That must not happen. That's a safety guarantee. A liveness guarantee is a guarantee that something good will eventually happen. Eventually, we want to like finalize the transaction, right? So eventually, we want all participants to either commit or abort the transaction. And now, taken together, right, that safety guarantee and that liveness guarantee basically states that eventually both participants come to the same conclusion. And that is fairly simple yet very fundamental example, because the nature of transactions is so important, not only in systems but also distributed systems. And it's a very tangible example, but it does turn out that the combination of safety guarantees and liveness guarantees is universal. Any set of properties of a system can be expressed as a combination of safety and liveness. Nothing bad must ever happen, something good must eventually happen. And what that also enables us to do is reason about failure cases. What do we want to guarantee in a case of a failure? Do we want to stick to adhere to our safety guarantees? Or do we want to stick to adhere to our liveness guarantees? So do we want to make sure that nothing bad ever happens, but that means we cannot make any more progress? Or does it mean, well, we do want to make progress, but now we cannot guarantee in that situation that we may not violate one of the safety guarantees? And that's, of course, a system design question, right? That's up to you, how you define correctness in general, and then also correctness in the presence of failure. And so it's a very powerful tool to explore your design envelope, right? What is your system? What is your system supposed to do? And what is your system supposed to do in the absence of failure, the happy path? And what is your system supposed to do in the presence of failure?
That's a great point.
There's a lot to uncover there. This is
Yeah.
it's a never-ending rabbit hole, especially combined with failure and how to
Yeah.
reason about failure. Is a never-ending rabbit hole that is very rewarding to climb in and out of, though.
Yeah. And also like correctness is another one too. Like what is correct? Should you, can you actually have partial state commit? Like you said, the transaction, right? Where people usually think about is all or nothing. I mean, not always the case. I mean, maybe it is worth it to at least write to the database that, okay, this user at least tried something, even though it wasn't successful. So we can roll back like a partial rollback. Yeah. And something else I think is also quite important that you talk about in your book and people don't always think about, including me, which is about like when you do send messages, right? When you do connect to another system and you want to do something, you want to send some data, there's like, what is it? Is there three different types of things you have to think about? It's like one and only one message, more than one message. Sorry, there's a third one in there, I think, right?
Yes, there is at most once, at least once, and exactly once, delivery and processing. And so that actually comes back. It's a great example of our office building. Right? What we generally, is exactly once delivery and processing. If I write a letter to Bob, let's stick to Bob. If I write a letter to Bob, I would like that letter to be delivered to Bob once. And then I want Bob to process whatever is in that letter once. So, for example, if Bob is in the billing department and I write to him to settle a bill, right, I want him to wire money to a recipient exactly once. So, turns out all we ever want is exactly once processing. Because if you have exactly once processing, everything else is basically completely trivial. It turns out we can't have it, right? So it's like there is a ton of information on the web that will tell you we guarantee you exactly once processing. They don't. Nobody does, because nobody can. Right? They can maybe guarantee you exactly once processing semantics in a very narrow setting, but generally you can't. Why? Why can we not do that? So let's say I sent Bob the letter, right? I sent Bob the letter. I want him to settle a bill. Bob needs to wire the money. in order for me, now, if we have exactly once processing, if I have the guarantee that once I put that letter into the nomadic tube, Bob's going to get it, right? Then I don't need a confirmation, right? So it's like I already have everything I need. The moment I send it, if I have the guarantee that it will be delivered once and Bob processes it once, I already, this is over for me, right? It's done. Cool. But if we have somebody in the mailroom and very nice colleague, but a little unorganized, and that colleague may lose a message, right? As soon as I put that letter in there, I actually don't know. I was like, now I don't know. The colleague may have lost that, right? It's like, is Bob going to get the letter and going to process it? No idea, right? So now I have a choice. First off, I can establish a protocol saying, hey, Bob, it's like, once you are done, send me an acknowledgement, right? Send me that receipt you did it. Now, unfortunately, that can also be lost, right? That receipt can also be lost. So it's like, now I just don't know. Was my original request lost? And therefore, Bob never processed the message, never got it in the first place. Or did he get it? He wired the money, but I didn't get the response. So now I have two choices. Even so, I want exactly once, I can't have it. Now I have two choices. One is at most once, and the other is at least once. So the message may be delivered and processed at most once. So either the message arrived and Bob did the thing, or it didn't arrive and he didn't do the thing. Done. All right. So it's like, I'm not at most once. I'm just not going to worry about that anymore. So if I get a receipt from Bob, I know it worked. If I don't get it, I actually don't know. If I don't get the message from Bob, I don't know if he did it or not. But I can choose not to take any other actions. Well, if we say, hey, wait a second, you're not taking any other actions, well, I may basically refer or kick the can down the road. Because if I don't settle the bill, somebody else will gonna send me a reminder, right? Saying like, hey, we didn't get the money. You owe us money still. And then I can do it again, right? And so on and so on and so on. But most of the time, that's not what we do. Most of the time, what we do is at least once, right? So it's like, if I don't get an acknowledgement from Bob within a time frame, let's say within an hour, if I don't get an acknowledgement from Bob, I'm gonna send this request again, right? So I'm gonna write another letter and I'm gonna say, hey, we gotta send money to these guys over there. So now I chose an at least once strategy, right? So it's like, I send my letter at least once. If I get a receipt, fine. If I don't get a receipt in a certain time frame, I'm gonna send it again. So at least once. But now we are obviously running the problem that Bob may have received that twice, right? So if he received the letter twice, then he sends money twice. Well, that's not good. So it's like that's the last thing we want. So therefore, I basically need to find a strategy that ensures that ensures exactly once processing semantics. So it has the same effect as if the letter was delivered exactly once. Now, how am I going to do that? We're going to combine at least once delivery with idempotence. Generally, I put a reference number on my letters, right? This is in regards to, or this is the invoice number 123. Right? So then when Bob gets the invoice number 123, he has his notebook, right? In the notebook, he writes, all right, I just got invoice 123 and I paid it. And then if he gets a letter again and it says, once again, invoice number 123, he can just look in a notebook and say, I already paid that. No worries about that. Right? That's what we call idempotent. So after the initial processing of a message, the reprocessing of that message doesn't have any other effect. So therefore, I just need to make sure that we do this at least once. And after that, we can do it 100 more times. Doesn't matter. Doesn't have an effect. Now, that's the gist of it. But that is in and of itself also fairly complicated. And it turns out that every other upstream component has to play ball. It's not only Bob, it's then also the bank that needs to be able to play ball to give you an end-to-end guarantee. So thinking about idempotence on a system level is not an easy task. Right? And if we think back into our original example where we say we only do an at most once processing, right? And then we kick the can down the road to whoever we owe money. When they send us a reminder, they also need to include that an idempotence key, so that in case Bob actually did get my original message, he can deduplicate on that key, right? So that is a fairly complicated interconnection of messages in order to make sure that we get this at exactly once processing semantic. And some days, I swear, that's basically like 99% of what distributed systems are. Yeah? Then at least it's like 99% of practical problems that you're going to face on an application level, because a lot of other stuff like distributed transactions, like very large message passing infrastructure and stuff is already taken care of. So that's already happening on a platform level. But on an application level, you have to deal with correctness issues as well, because there are end-to-end guarantees. And so on an application level, it feels like 99% of your brain power is going to be spent on making sure that everything happens exactly once, or equivalently to exactly once.
I remember about that stuff, right? I remember also seeing things like a nonce, things like that. I mean, there's ways that you could do this, kind of make sure that there's only ever one of these requests. And I think that's a really great one to have when you have like an unreliable connection between devices, like such as we're going back to, Flutter, right? With mostly on a mobile network. Mobile networks are always really, really bad. I mean, I had a user of an app I was working on, and he was on an island because Hong Kong has lots of islands, and he always had an issue with connection. I mean, he's on an island, right? So things are bound to happen. Since we're kind of approaching the end of our time, I think it would be good to kind of end our discussion with, if you have some kind of like tips for when we are making our API, how can we kind of ensure, because to me that most brittle part is that connection between the phone and our system. How can we really ensure that we're getting we're properly doing what we need to be doing, if you don't mind?
That is already a fairly deep question. But on a very high level, what I always recommend is to think in terms of message passing. And you, I believe, also mentioned it, at least we talked about it before the podcast. And I think you also mentioned it during the podcast, message passing being a big part of the Erlang and Elixir stack and philosophy. So think in terms of message passing. Do not think in terms of connections. TCP connections, right, are not the way to go. Now, of course, you will be opening a TCP connection, right? That is not the question, because that is generally our underlying communication protocol. But the semantics you should implement is a message passing semantics, not a connection oriented semantic. What does that mean? That means is like, do not attribute too much that particular connection. Do not use that connection to identify messages or retry messages. So one way of doing that, make sure that the client already adds a key and be used as a key on them for to identify a logical message, even so if that message gets sent physically multiple times, and if in doubt also over different TCP connections because one just dropped. Right. So that is my recommendation on a very high level. Start with the client adding IDs that can be used as idempotent keys. For the very first step in the processing pipeline, adds an idempotent key, and then treat that thing as a message, where it doesn't matter how that gets to the server and on what connection that gets to the server, as its own basically letter, right? That identifies itself and identifies the process that it works on, just like the invoice, where if I get 15 copies of that invoice, it doesn't matter how, whether it's delivered via the nomadic tubes, whether it's delivered by a mailman, or whether somebody storms into my office and shoves it into my face, I know what this message is, or what this particular letter is in regards to, and can from there on process it. So the very, very first step should be create an idempotent key, and from there on treat that message as message passing, never attribute anything to that connection.
Yeah, sorry. I think I had a little bit of an interconnection problem, but it sounds like if case this comes out bad, like you're really talking about making sure you have an idempotency key to make sure that send it the message quite a few times just to make sure are not missing something. I think that's a good point. The other thing I have to say about that one is you need to be careful, at least on the client side, that you're not keep popping up, like a confirmation message. This worked, this worked, this worked, this worked, something like that. So I guess there's something I would do on the client side, make sure that we're not annoying the user, right? Because I remember getting those messages. I'm like, I get really annoyed, right? So, but yeah, sorry, you were going to say something.
Deduplication is a tough issue. It's really not straightforward, and every single component has to play ball in order to get that right. And if one component basically drops that ball, you may run into the issue now where you pop up with 17 confirmation messages because you just cannot establish the identity, the logical identity of that message. You're basically getting 17 physical messages. You cannot establish the fact that they're all the same logical message, therefore keep bugging the user. It's very, very quick for that to happen.
Yeah. But again, at the same time, I mean, it's better than like confirming it's okay and then you find out it's actually not okay. You got like a false positive,
Yeah, that is
worse.
about the worst. Yes.
Yeah, I had that today where like I needed to top up my Starbucks card to just get a coffee this morning, and then it said it didn't work, and then all of a sudden I got a message from my bank saying that they took money from the card. I'm like, wait a minute, and then finally I had confirmation that it worked. I'm like, what the hell's going on over here? So it was,
and now we have a safety violation. Something bad just happened. Unless, of course, and chances are high that it is also structured around eventual consistency, where there is a, let's say, best effort communication between the card and the bank. But then there are also reconciling protocols in the background that then eventually will make sure that this balance is either reflected on the card or the bank will revert the transaction. So yeah, it's super, super interesting. Very, very cool topic to work on, especially if you combine it with user-facing processes and user-facing applications, right? Because then you are adding a third variable to the mix. You have liveness, you have safety, and now you also have a user experience. And these three can be, and often are, in stark conflict with each other, right? So you have to make trade-offs.
Yeah, that's a very good point. Yeah. That's why I like books like yours, because it's not so like, oh, just do this, just do that. No, because it's very complicated, right? I mean, to give some more detail about this morning, we don't need to expand more on it, but just like I was topping up through Apple Pay. So we have myself using a cell phone on 5G. I'm talking to Apple Pay that has to talk to the Starbucks app, that has to reload the card. There's so many things that can go wrong in here. So it's interesting. I'm kind of curious to see how they did it, but all I know is that my experience was not good until I finally got my coffee. Then I felt better. But seeing the error and then seeing success, yeah, the whole world is on digital duct tape. Basically, I think you know this already. So
I had A similar experience, and I think, and that experience also made an appearance in the book because it just stuck to me so much. I was booking a flight, and the app of the particular airline was glitchy, right? And so it would error out at a certain point and then restart. And then I basically made my way through it again. And I did this a few times. And then I received the messages of the charges. And it turned out that it charged me many, many times, or it charged my credit card many, many times, right? For this one ticket. Now, obviously, I was not happy about that, having no ticket, but having been charged many, many times over, right? So, of course, one of the first things I did is I called the airline. They assured me that yes, the ticket has been granted. It's only one ticket. And they also told me that within about 24 hours, these multiple charges will reconcile into one, right? So they gave me the guarantee that eventually, right, my one ticket will be charged exactly once, and the charges will actually not show up on the credit card. There were holds, right? But my user experience was absolutely terrible. Even so that the system turned out to work correctly, right? The user experience was horrible because obviously you're sweating bullets when you get charged multiple times for like one ticket, and the ticket is usually like a substantial amount, right? So then, yeah, while safety and liveness were ensured, yeah, the user experience was anything but optimal.
Well, I mean, also too, like it's also not a great experience for a user because if they're holding that charge in your card and you reach your limit and you need to use your card for something, you're as we call SOL, which I think you know that term. You know,
Yeah,
so
exactly.
that's it is nice that you do get the money back, but at the same time, not nice if you need to use your card and you can't because you're going to be over limit, right? Because you're holding the money.
Exactly.
Yeah.
Exactly.
Yeah, but before we go on for, days and days about distributed systems, yeah, I think yeah, we've reached the end of our time. I think your book is really great. It seems to break down a lot of the difficult concepts into much easier to understand examples. Like I said, I really love that office building example. It makes it quite clear to see actually how this stuff works. And it's good to talk about, like I said, this system being a bunch of concurrent processes, each focusing on one small thing, right? But overall work together to achieve a common system. Is there anything that you wanted to say before we end our session?
There is a very interesting concept that helped me a lot in reasoning about systems. And that is the concept of a holarchy, not a hierarchy, but a holarchy. And a holarchy allows you to think in messy hierarchies, basically, many layers of complexity that don't just neatly unfold into a tree of neat components on a lower level. And the core concept of a hierarchy is a holon, something that is a whole in and of itself, but also part of something bigger and composed of something smaller. And the concept of holarchies is not very often talked about, but it is an incredibly cool reasoning tool because it allows you to basically just jump layers and look at a set of components as one component. Um, but you can also basically fluidly allow other components to join that set or leave that set and use that lens to understand your system from many, many different angles and many, many different layers. So that concept of holarchy and holon is one of my favorite reasoning tools about distributed systems that I would recommend everybody to at least look into it a little bit. And even if it's just like, for example, the Wikipedia article, yeah, or the chapter in my book that talks about holarchies, it's a very, very cool reasoning tool that allowed me to reason about distributed systems very efficiently and with great accuracy. So that I recommend to everybody check that out. And right after that, do spend just some time out of curiosity to look into formal modeling as a reasoning tool, because it will allow you to sharpen your understanding beyond studying code, because code is generally a very low signal to noise ratio. Formats have a very high signal to noise ratio with your understanding.
Okay, some great tips. Yeah, but again, we're having a little bit of connection issue at the end. I think there's something with my side. So after this one, I have to go restart my router. It's not your thing. It's on me. It seems to be. So I apologize about that. Hopefully, this recording worked out good enough that we can scramble some of that great information you said today. Yeah, again, otherwise, thanks for coming on. We will have a code for this book, so that way people can, who are interested in picking up the book, will get a nice discount. I also just want to say again, please buy the book from Manning. Do not buy from Amazon, because then more money goes into his pocket, and then he'll keep working harder on the next book. Thinking Distributed Systems Part Two. Sounds like you have more information you could be saying. I don't know if you're ready to write a part two or not, but just in case.
Yeah, I'm going to take a break. I'm going to take a break.
Yeah. I tend to think that like writing books are kind of like having kids, at least, in terms of like the whole process, because it's like, you're excited, you're working on it, and then it's exhausting. I never had a kid, but this is just the way I'm thinking about it. And then once you have the kid, once you release the book, you feel great. And you look it back, you're like, actually, it wasn't that bad. And then you do it again. And then you're like, oh, actually, it was that bad. And then you finish it. Okay, maybe not so bad. Like, it's just kind of teeter-totter of, when you're in the process of doing it, not nice. When you release it, okay, that wasn't so bad. That was actually kind of nice. I enjoy this product of what I worked on.
It's like I very much enjoy the product that I work on, but I have not forgotten. Yeah, it's like I'm not in that state yet where I'm like, oh, that wasn't so bad. But I'm still in the state of like, man, that was horrible. But I'm very, very happy. Yeah.
I'm sure it'll happen. I don't know. Maybe I'm wrong. Maybe you have a better memory than me. But it seems like a lot of things is like that wasn't that bad. And you look back on it, and but anyways,
it's
yeah.
true.
So
some of it is already fading into the background, but I'm not over the hump.
So not yet. You're still in the. I guess it'd be the opposite of a honeymoon phase. I'm not sure what that was called. Recovery phase, I guess.
Exactly.
Yeah. But then again, thanks for coming on. It was great to meet you and to talk more about distributed systems. Huge fan of that. And yeah, so for you guys listening out there, definitely pick it up and give it a good read. It's a great book. And I guess maybe one last thing would be, if people are interested to get in contact with you, what's the best way to reach you? Is it X, or is there something else that you usually use?
Yeah, X is where I hang out the most. X and Blue Sky. I'd be happy to chat. The DMs are open.
Okay, sounds good. Again, thanks for coming on, and hopefully we'll have you again on in the future.
Hey, thanks for having me.